Hello and welcome back to the second installment of this video series working on this Predator engine. And in this video I'm not going to be doing any fabricating or building. It's really only going to be explaining the camshaft that I'm putting in this bike. And I'm going to be comparing it to the stock camshaft and explaining the different terminology commonly used in camshafts and what it all means and how it applies to how much power an engine puts out and how it applies to the build that I'm trying to do here. Alright, now before we continue any further, I think it's important to explain what the difference is between the cam that I bought online and the one that comes stock in the engine. So the cam is a pretty important part of the engine. It's commonly called the heart of the engine, and that's because it controls the valves, which controls the combustion, and when the exhaust and when the intake gases are leaving and exiting the chamber. Alright, now before we continue, it's important to understand the four different stages of a four-stroke engine, which is what I'm working with and is what most engines have. There's also a two-stroke variant, which is half the steps, and I won't explain that in this video, but it's mostly used by things like maybe dirt bikes or more of like maybe boat engines. It's usually not used as much. Four-stroke is definitely a more widely available and much more common option. So the first stage or stroke of a four-stroke engine is the piston is being lowered and it's creating a vacuum, and when this happens the intake valve opens up. It's being pushed down, and when that happens the air fuel mixture is able to enter into the combustion chamber. So as that piston comes down, it creates a vacuum and it's able to pull an air fuel mixture from the intake port because the intake valve is open. In the next stage of a four-stroke engine is the compression stage. The crankshaft is then pushing the rod, which then pushes the piston as it moves up into the cylinder. And what this does is it takes this previously air fuel mixture, which was at about 1 atmosphere, which is what the Earth is at, so it was not really compressed. As this piston moves forward, it has a seal, so it's a very tight seal. As this piston moves forward, it's going to compress this this mixture of gas into a much smaller space. So it's much more compressed, and then the spark plug is going to ignite this air fuel mixture. The third step in this process is the combustion phase, and it's the most important piece of this. So as I said in stage 2, the spark plug is going to ignite the air fuel mixture, and what that's going to do is it's going to explode. And this explosion is going to be contained by the piston and by the cylinder, and everything is sealed shut. And that's important. This gas has nowhere to go except to push down on the piston, which then pushes down on the piston connecting rod and then the crankshaft, and it's turning that linear motion into a centrifugal motion or rotating motion, and that's why this type of engine is able to power cars and other things like that. So this air fuel mixture is ignited, and it combusts and pushes down on the piston. This is also called the power stroke. And in the final stage of this type of engine, we have the exhaust stroke. So then the momentum and the inertia from the crankshaft is going to push the piston right back up, and it's going to push the spent air fuel mixture, which is now called the exhaust. It's just carbon dioxide at this point. It's going to go out through the exhaust valve and out the exhaust port. So the exhaust valve is open. And it's important to realize in all these different stages, the only two that have a valve open is the first stage, where the air fuel mixture is being introduced into the engine, and the last stage, where the exhaust valve is open and this spent air fuel mixture is being pushed out of the engine. It's also important to realize the only stage here that's creating any sort of energy is the third stage. These other three stages are only happening because the inertia from the crankshaft is able to push and pull on the piston as it moves. So there are a few terms that you're going to want to understand in order to understand how a camshaft works and how altering the shape of a camshaft can alter the performance of an engine. So for the first key term we're going to want to look at is going to be lift. So the lift is referring to how much lift or how tall these little cam profiles are. And if we look at the stock cam versus the new cam, you can see that the lobes on the new cam are much taller. And what that's going to do is it's going to push the valves down further. So as I discussed earlier, with the valves letting in air and letting air out, what that's going to do with these taller profiles is it's going to push those valves down further, which is going to create more airflow in the engine, meaning it's going to be able to breathe easier, and it's also going to be able to get rid of the exhaust gases much more efficiently, and it's also going to be able to take in an intake of the air-fuel mixture a lot easier, and it's going to be able to get more of that mixture. The next important term we're going to discuss is the lobe separation angle. And the lobe separation angle is referring to the top of the intake lobe to the exhaust lobe, and it's referring to the degrees between the top of both in relation to the camshaft. So this camshaft needs to turn, in this case, 110 degrees for it to get to the top of the intake lobe to the top of the exhaust lobe. And typically with an engine, it's going to range between 104 and 115 degrees. And depending on how you set it, it's going to have a different impact on the engine. So for an example, 104 degrees is about as low as you're going to want to go. And what that's going to do is it's going to increase your valve overlap. So during the process of the 4 stages of a 4-stroke engine operating, the intake and the exhaust valves are going to be moving. And there becomes a point when both the intake and the exhaust valves are going to be open at the same time. And by setting your lobe separation angle to a very low degrees, so for an example 104 degrees, what you're doing is you're increasing that valve overlap. You're increasing the amount of time that both valves are set open. And what that's going to do, if you, for an example again, if you set it at 104 degrees, it's going to increase the pressure inside of the cylinder, because there's going to be a lot more gas in there, because there's going to be more opportunity for gases to come in and out. And what that's going to do is it's going to create a low RPM range, meaning you're going to have less horsepower. The engine is going to rev a lot lower, but you're going to have a lot more torque. Now on the other end of the spectrum, we have the higher degrees of lobe separation angle. For an example, 115 degrees. 115 degrees is going to decrease the valve overlap. So the amount of time that both your intake and your exhaust valves are open. So it's going to be a lot more separate. Those 2 stages are going to be a bit more separated. And what that's going to do is it's going to decrease the pressure inside your cylinder, but at the same time it's going to increase your horsepower. The engine's going to run a little smoother, and it's going to allow the engine to rev a little higher. So you're going to have more horsepower, but at the cost of having less torque. So for the application I'm doing here, I chose 110 degrees. So this was about as high as the website NR Racing, I believe, had this set to go. So for my mini bike, the sprocket is big, and I have a lot of other components that has given this bike a lot of torque, such as a 12-tooth clutch and a sprocket. I'll have to include a picture. A sprocket that is almost the same size as the wheel. Meaning for this application, I didn't really want to add any more torque, and I wanted to add more high-end horsepower. So I chose the 110 lobe separation angle to give me more horsepower. And if you look at this cam, this might help a little more for understanding. You can kind of tell this doesn't have a ton of valve overlap. If you look at the profile of these 2 cams, there's not much distance where both of these are going to be open. So if this is 104 degrees, these would be pushed together a little more, and there would be a much more noticeable overlap between this lobe and this lobe. The next term we're going to discuss is duration. And before we go any further, it's going to be important to realize that for every 1 rotation of the camshaft, it's going to require 2 rotations of the crankshaft. And why that's necessary is because if it was a 1-to-1 ratio between the rotation of the crankshaft versus the camshaft, you'd be having your intake valve open during your combustion phase. And at the same time, you'd be having your exhaust valve open the compression phase. And that really would defeat the purpose of the engine, as there really wouldn't be any way to compress and combust the air-fuel mixture. So it's important to separate that out at a 2-to-1 ratio so your valves are opening at the proper time. So this, what this means is that it's referencing how long each valve is open in relation to degrees of rotation on the crankshaft, not the camshaft itself. So the duration here is 260 degrees. That is talking about the crankshaft. Now, if I wanted to get that figure in relation to the camshaft rotation, I can just cut that in half. So we're looking at about 130 degrees if we're talking about rotation on the camshaft, or 260 degrees if we're going to be talking about the crankshaft. And what that's referring to is how long that each valve is going to be open. And it's measured at 5/100ths of an inch. So that means, and it's all starts with the shape of these lobes. So that means that the intake valve is going to be open from when it opens to 5/100ths of an inch to closes to 5/100ths of an inch. It's going to be done on 130 degrees of rotation on my camshaft, or 100 or 260 degrees on my crankshaft. So the next important term is the intake center line. And the intake center line is referring to when your piston is going to be at its top dead center, meaning it's going to be as far as it can go. So for this case, we will use the fourth stroke. So as this fourth stage occurs, it's going to be pushing out the spent air fuel mixture, or the exhaust. And this valve is going to close, your exhaust valve is going to close, and it's going to push up, and it's going to reach what's called top dead center. And that's when the piston is as absolutely far as it can go. And from that stage, the piston will then, again, drop down. This cycle will restart back to the first stage. And this is then going to pull down, again, create a vacuum. And this intake center line is referring to how long it takes for this piston to go from its top dead center to the valve to open up. Now you want there to be a delay, because if you had your valve open up when the piston was at top dead center, you'd have your valve hitting your piston, and that can cause a whole lot of issues with the piston. It's going to damage the piston. It could bend the valve, and it's really going to ruin your engine. It can be, and depending on your engine, it can be thousands in damage. For the ones I'm using, it's just a matter of shelling out another $80 for another engine. But it's also in relation to the crankshaft rotation, which is also important to realize. Not the camshaft rotation, but the crankshaft rotation. So it takes 108 degrees of the crankshaft rotating for the intake valve to open up to its maximum point, which again is going to be at the top of this lobe. So for this to open up all the way, for the exhaust, or for the intake valve to open up all the way from the point of when your piston is at the very top, or top dead center, it requires 108 degrees of crankshaft rotation. Now, when comparing these two cams together, I know all the specs of the aftermarket cam, but know next to nothing about the stock cam. I've called around, looked around online, and the only thing I could find is people think it's around a 225 lift, which is quite a bit different from my 292. And I don't think I mentioned it, but lift is also measured in thousandths of an inch. So this is 292 thousandths of an inch, 225 thousandths of an inch. I have no idea about lobe separation angle or intake center line. I have really no information. I don't think they even publish it online. But if you look at the lobe separation angles, they look about the same. Again, it's going to be hard to tell 1 to 2 degrees of difference, especially on a YouTube video, but even in person, I really can't tell all that well. So this could be 110 degrees, like my aftermarket. Could be 108, could be 104 for all I know, but I doubt it's that low. So if I was to guess, this is probably 108 degrees, as that's considered like a happy medium. I get the best of both worlds, having good torque, also high-end RPM application. That's going to be it for this video. The next video will be a little more hands-on, continuing the build, taking the engine apart, and then doing a little bit of custom fabrication later on, trying to make sure the valve springs seize. So stay tuned for that. But the next video will be a little more hands-on with building and such. Thank you.